Welcome back. So another example is what we call a button press synchronizer. And the description of this circuit is there is a circuit that synchronizes a button press to a clock signal. It's something like this, that a user presses the button and that button results in a signal that is high for exactly one clock cycle. Right? Now let's try to understand this circuit from the timing diagram here. So here in the red, I have clock. Again, I'm assuming that my clock responds to the positive edge, means these edges. And I have how means this is first cycle, second, third, fourth, and 5 clock cycles here. Then to represent the button press, I'm using the input BI, wherein the high pulse states that the button is being pressed, and the low pulse means that the button is being released. Fine. Now the circuit says that the output of this particular circuit, it will be something like this. See, up to this point the button is being pressed here, fine, and after the button is being pressed the clock rises here. So up to this point your output will be 0, fine, and when the positive edge of the clock comes it will check what is the status of the input, whether the button is being pressed or released. Now here the button is being pressed, so output will go high, but the description of the circuit is such that even if I am continuously pressing the button, like here I am continuously pressing the button for multiple clock cycles, but the circuit has to be such that this output should go high for only one clock cycle. Then later on when the button is released as is here, then again if it is pressed like it is here, it will again go high for exactly one clock cycle. So this is the description of the problem. The key catch here is that the output, let's say B naught, that is the output of the circuit, it will remain high for exactly one clock cycle, regardless of the fact whether the button is being continuously pressed for multiple clock cycles, whether the button is being released immediately. Fine. So the output will remain high for one clock cycle. So we have to design. It's a very important circuit in the control circuits, and we call this button press synchronizer. Fine. This is going to be an important circuit because I'm going to introduce a very important concept here with regard to finite state machine. So I thought instead of directly introducing the concept, let's take an example, and using this example, later on I will introduce a very important concept as far as finite state machines go, as far as design of FSM goes. Now let's design this circuit. So as usual, the first step, we have to capture the finite state machine. Fine. And let's start with the state. Let's call this state, let's say state A, and let this be my initial state. Fine. And let this be the state wherein the output is 0. So B naught is equivalent to 0. Fine. Now from this state, two things can happen. First, I will press the button. Second, I will not press the button. I will keep the button in the released state. Fine. Now, if the button is in the released state, that means I will stay in the same state, which means my output will be 0. So it is represented by this transition. This happens when I am not pressing the button. So I am putting BI complement. Fine. But second scenario can be wherein I press the button, BI. Now when I press the button, my output goes high. So I will introduce another state. For the time being, let's call it state B. And in this state, my output B naught is equivalent to 1. Fine. Now again, two conditions can arise in this state. Okay, output is 1, but the thing is that our circuit should be such that the output has to be 1 for exactly one clock cycle. This means from this state, state B, I will only remain in state B for one clock cycle. And two conditions can arise. If I continue to press the button, so something like this, I have reached the state B, stayed here for one clock cycle, but I am continuously pressing the button, which is actually being depicted in this timing diagram. I am continuously pressing the button. Then I will have to look for a third state, time being, we call it a state C, wherein my output will again be zero. Fine. This is the first condition from state B. Another condition can arise, okay, I have pressed the button, I have reached the state B, but here I stay for one clock cycle, and immediately after one clock cycle, I release the button. In which case, again, my output is going to be zero, but I will move to state A. Fine, because state A is basically when the button is released. Right? So in both cases, whether the button is being continuously pressed, whether the button is being released, my output is going to be zero. It is going to stay for one clock cycle, then it's going to be zero, but the states will be different. Fine. If I continuously press it, I will go to state C, and if I release it, I will come back to state A. Fine. Now, as far as state C is concerned, again, two things can happen. If I still continue to press the button, then I will stay in this state forever. So this happens for BI. But if I release it, then again, I will come back to my original state A. Maybe I can show it here. This also happens for BI complement. Right? So this will be the finite state machine. Right? So I have to introduce the state C, because whether I continue to press the button or whether I release the button, output will always be zero. But the transitions will be different. From B to A will happen when I release the button. From B to C, it will happen when I continuously press the button. And even after reaching the state C, you see, these transitions, like I told you, happen with clock cycle. I told you that clock is always implied. So when I move from A, when I say state A to state B, it means from one clock to next, as shown here. So state A is something, sorry, state A is what the status of the circuit is in first clock cycle. State B, this, and so on. Fine. So this will be the finite state machine of the button press synchronizer. Fine. I have the initial state A where output is zero. If I don't press the button, I will continue to stay in this state regardless of the number of clocks. But if I press the button, then on the next rising edge of the clock, I will move to state B where my output is going to be 1. But thing is, the circuit is such it will only keep the output for one clock cycle. So my stay at state B is for one clock cycle. From B, I will either move to C if I continue to press the button, or I will come back to A if I release the button. Fine. Then in the state C, my output will be zero. If I continue to press the button, I will stay in the same state. If I release the button, I will come to state A. Fine. So state A, the transition from B to C is when you release the button. So that next time when you again press the button, you can move from A to B. So this completely captures the behavior of this circuit. Fine. The next step is we have to create the standard architecture. Now I have three states. For three states, I will at least need 2 bits. So standard architecture will have a 2-bit state register. Let me draw it on this side. So there will be a 2-bit state register with a mandatory clock. And there will be the combinational part, which we will resolve later. So this will be my combinational logic. From the state register, I will have 2 outputs that will serve as inputs to the combinational logic, S1, S0. Fine. And I will have 2 next states N0 and N1. Fine. So this is S1, S0, this is N0, N1. And then I will have an external input which I have named as BI and an external output which I have named as B0. So this is the standard architecture. Then third step is encode the FSM, wherein you will have the same state machine. Instead of using the alphabetical names, we'll be using a unique code. So let's this have a code of 00, 01, 10. Rest of the things they will stay the same. The transitions, the initial states, they will remain the same. So this is still my initial state. I will continue to stay in this state for BI complement. I will move from here to here when BI is high. Then I will come back to original state 00 for low value of BI. This happens for BI, BI, BI complement. Fine. And the outputs are defined. Once you are in the state A, which has been coded as 00, your output is always going to be 0. Once you enter the state B, which has been encoded as 01, your output is going to be 1. And state C, for which I have the code 10, output is going to be 0. This is a very important feature. In fact, up to this point, whatever state machines we have designed, once we are in a particular state, output is defined. You can look at previous examples like this one. I was in state 00, output was 0001. It was not conditional. It was implied once you are in this state, this is my output. Similarly, when I move to state 01, 0011 was my output. Right? So this is we have been designing up to this point. Given a state, output is fixed. Fine. So this is the uncode FSM. Next step is we have to create a state table which will help us to resolve our combinational logic. So state table may I will have two state outputs. So I will list input. So this is the fourth step, creating the state table, and I will list my outputs. Inputs, I have two state inputs, S1, S0, and then an external input, BI. Outputs, two state outputs, N1, N0, and an external output, B0. Fine. So then you can fill the combinations. Initially, I am in the state 00. Fine. And if I am not pressing the button, I will continue to stay in the same state. My output will be 0. If I am the state 00, but I press the button, I will move to the state 01, and my output will be still 0 because I am still in this state S1, S0. Fine. But when I am in state 01, fine, first my output will be 1 in this state. Then if I don't press the button, if I release the button, I will come back to the state 00. Fine. If I am the state 01, but I continue to press the button, my output will be 1 because it is defined by the current state, which is 01. But I will move to next state, which is 10. And when I am in 10, if I am releasing the button, I will move to the initial state. Since I'm in state 10, output will be 0. And similarly for the same state, but when the button is being pressed, I will continue to stay in the same state and my output will be 0. Fine. And if you see with 3 variables, I should have 8 conditions. Fine. But I have defined only 6. So 2 conditions are missing. And those conditions are 1001. Let me put them in a different color. 110, 111, because there is no 1 state. Fine. So you can treat them as don't care. Fine. And from here you will get the equations. Let's first solve for B0. B0 will be this. So that would mean S1 complement S0 BI complement. And this term will be S1 complement S0 BI. If you wish, you can take care of, you can exploit these, use the three variable K map and get it in the simplified form. Fine. But I think you can also use the Boolean laws here because some things are common here. Like I can take S1 complement S not common, that will leave BI complement and BI. Then this will mean S1 complement S not. Fine. So simplification you can do in multiple ways. If you want to exploit don't care conditions, you can also do that. But I'm not fixating on that because those things you can do, you have learned them. Similarly, N1 will have an equation. Again, I will directly write the equation S1 complement S naught BI plus S1 complement S1, wait up, no, it is S1, then S naught complement for this and BI. Fine. Again, if you'll simplify it using Boolean laws, it will end up with this BI S1 XOR S naught using compound gate. Similarly, you have N naught. N naught has only one high term, so it will only have one term S1 complement S naught complement BI. So these are the three equations and they will resolve my combinational logic. You can easily implement them. So we'll do it here only. We don't need the table. So let me get rid of the table and we will draw this circuit here only. If you wish, you can further simplify it using don't care. Those things you can do at this stage. Huh? Okay, so we already had the sequential part resolved, wherein I had a 2-bit state register. So that is there. This is my 2-bit state register. And from here, I will have my S1 and S0. Fine. Then I also have an external input BI. So this is my external input BI. So let's name it. This is BI and these two S1, S0. This is a 2-bit state register with a mandatory clock. Fine. So first of all, the output B naught. So it will be S1 complement and S naught. So this is B naught. Then N1 will be S1 XORed with S naught. So here it is. Then the output will be ANDed with BI, something like this. So this will be N1. It will come here downwards and be connected here. And N naught will be S1 complement. Here is S1 complement. S naught complement. Here is S1, S naught complement. Then a tape from BI. All these three I will combine using an AND gate that will be fed back here. So this is my button press synchronizer. Fine. Now an important observation here is, and that's also the observation for the previous circuits that we designed, is that in the FSM, once you enter a particular state, be it A, B, or C, your output, external output, I mean, is defined. Like in this case, when you enter A, B naught is 0, regardless of what the value of input is. When you enter the state B, B naught is fixed as 1. And when you enter the state C, B naught is fixed at 0. So those machines, those finite state machines, which are coded like this, where in the finite state machine, what do you say, where in the finite state machine, the individual states have a fixed output. These are known as the Moore machines. Fine. So you can say Moore machine is a machine wherein the output in a particular state depends only on the present state. You enter a state, you will have a fixed output. And if you capture your circuit, if you capture the behavior of your circuit using a finite state machine where the individual states have a fixed output, we say this is a Moore machine. Fine. And the outputs in that case are called Moore output. Fine. So here, this is a Moore output, Moore output, Moore output, and overall the state machine is a Moore state machine. Fine. Let me just get rid of these slides. And there's another way of capturing the behavior of the circuits, which is slightly difficult, wherein we capture the behavior in such a way that the individual states they don't have a fixed output. Let's try to understand this. Like in this case, I'm in the state A, regardless of what is happening at the input Bi, my output is 0. I'm in the state B, regardless of what is happening at the input Bi, my output is 1. So once I enter a particular state in a Moore machine, my output is fixed. But there is another way of capturing these sequential circuits, capturing the behavior of the sequential circuit, and that is known as a Mealy machine. So we have this Moore machine. Second approach is what's known as the Mealy machine. And a Mealy machine is a machine wherein the output of a particular state depends on two things. First, it will depend on the current state, in which state you are, but it will also depends on the current state and the external input. Fine. So that is known as a Mealy machine. So we'll stop this video here. Next video, we'll do the same example, the button press synchronizer, but we will capture the behavior using a Mealy machine.